So once again, welcome to the Webinar Wednesday presentation of powering up the motorsports industry with SOLIDWORKS Flow Simulation. My name is Damon Tordini. I'm the product manager for Flow Simulation here at Hawkridge Systems, and we're going to be taking a look at how this product, SOLIDWORKS Flow Simulation, can be used specifically when you're designing components or other products related to the motorsports industry, where you might want to check if the design aspects you're coming up with are going to improve performance or change airflow, change temperature or heat transfer in some way in order to create something that performs better and of course maybe captures more market share, and be able to do that without necessarily having an expertise in computational fluid dynamics or having to rely on a dedicated analyst to do this type of analysis separate from the design process. So most of us probably have looked at a dynograph at one point or another, whether that's for a motorcycle or maybe the car you drive at home. But of course, one of the key, kind of market forces in the motorsports industry is figuring out what company can come up with the best new aftermarket product or even new vehicle that ekes out a little bit more performance, just a little more horsepower, a little more torque, maybe pushing something to the limits of what you can do. And so we all know that, of course, the results of a dyno are sort of the proof that most of your customers will want in many cases, to kind of see the result of something. And that's invaluable when you're designing and manufacturing a new product, right? The real world test. But when you're going through a product development cycle, we all know, of course, that there's no way you could practically make a bunch of prototypes for a product and go submit it for dyno testing every single time, right? The cost of dyno testing is a factor right there, but even in addition to that, just the time and money required to make a new prototype every time you want to try a different design change or you have a new idea, it just makes that impractical. So to make sure that that dyno test is as good as we can get it, we ideally would have a solution to test a bunch of different ideas up front while you're in the design process in SOLIDWORKS to figure out sort of what maybe the one or two best ideas are that we can then make a prototype for, throw it on the dyno, and really get that real world evidence that you made a new product that improves something and is worth the money. And so, of course, the type of analysis that is used to simulate any kind of fluid flow problem, like airflow in an engine, is called CFD, computational fluid dynamics. And so in the SOLIDWORKS simulation family, we have a variety of simulation tools that are integrated into the CAD package of SOLIDWORKS. And one of them is called SOLIDWORKS Flow Simulation, which performs this type of analysis, performs CFD. There are some other tools we offer at Hawkridge Systems, like Simulia Abacus, which have certain kind of limited flow characteristics in it as well, and maybe capabilities for certain types of flows, especially as they interact with maybe a stress analysis. But if you're talking just about the aspects of an airflow simulation, whether or not you've got pressure buildup or what's happening to velocities or turbulence or anything like that, SOLIDWORKS Flow Simulation is generally the best solution, especially if you're designing in SOLIDWORKS and you want an easy-to-use solution that doesn't require someone to learn a new program or to add more steps to their design and analysis process. This is going to be as streamlined as possible. So what exactly is flow simulation? Well, it's a general-purpose fluid flow tool which includes heat transfer, which means that it's not intended just for one type of simulation or one type of product or one type of industry. It can handle a lot of different types of problems across a pretty big range because of the capabilities that it has and because of the meshing technology that's built into the tool that makes it able to handle pretty much any kind of geometry you would want to create in SOLIDWORKS. So it's, of course, a 3D design simulation tool so that you can analyze the actual geometry that you're creating and are planning on manufacturing. And it couples not just fluid flow, but also heat transfer together so that you can evaluate almost any of the performance characteristics that would be important, especially in a situation like aftermarket components for motorsports. If you want to know if you're getting more airflow into the engine, or if you are lowering the temperature and maybe densifying the air, or you're getting the right kind of exhaust velocity. All these aspects are part of the capabilities of the program, but what's maybe even more important than that is the fact that it's fully integrated into SOLIDWORKS and very easy to use as far as setting up where the fluid regions are in the geometry and meshing and capturing those fluid regions without a lot of manual work, so that you don't have to be any kind of CFD specialist to use the tool, and you can take these analysis results while you're creating a design in the first place in SOLIDWORKS and obviously use that to make the right decisions. And in particular, there are a suite of capabilities in SOLIDWORKS Flow Simulation that are going to be really important for a motorsport application like this. Of course, you can probably tell right away just looking at this image that depending on what component you were designing on a vehicle like this, there might be 4 or 5 different fluids in that image. And SOLIDWORKS Flow Simulation can represent all those different fluid types. Gases to represent air or exhaust, liquid to represent coolant, like for example Freon or fuel, and even non-Newtonian fluids to represent things that have high viscosity like oil, which might be changing depending on the shear rate in the different parts of the engine or the temperatures. And so we can simulate almost any aspect of this vehicle. We can also do both internal and external flow, including turbulence. So if you wanted to simulate, for example, aerodynamics around the bike or around maybe the rider's helmet, or even, this was maybe a motocross simulation, and you wanted to, or autocross, and you wanted to simulate, for example, a wing or other aerodynamic surfaces, you could get all of that data, including the lift and drag and other reactions. And most importantly, all of this stuff can be simulated with the heat transfer fully integrated into it. So, for example, if you're trying to figure out what kind of heating is going to happen in the brake rotor, that is something we can figure out by including conduction and convection in the simulation. Maybe you're trying to design a new rotor with the right kind of slots to improve cooling. And so let's start by taking a look at one example here. This is a motorcycle muffler. And maybe the question in this type of a product might be, how should we design the core, the perforated metal core in the muffler, to improve the exhaust flow, maybe make sure we don't have excessive back pressure, make sure we're getting the right velocities, exit velocities, for optimal engine scavenging in the header, for example. And also, what is it going to do to the noise? And so what we can do is run a simulation in Flow to predict all of those pressure and velocity results. And if we make it a time-dependent simulation, we're also going to get some of that acoustic information as well. So let's take a look at SOLIDWORKS here. I'm going to open up SOLIDWORKS 2018, which is the latest release. And so here I've got my exhaust main body component that I've modeled up. In this case, it's just a part file, but it could be an assembly too, doesn't matter. The only requirement as far as using flow simulation is that you need to have solid geometry. So that could be something you model in SOLIDWORKS, of course, or something you import from another file type, as long as it's a solid body that we can work with. Now, when you want to run a simulation in SOLIDWORKS Flow, the main question you have to answer for yourself at the beginning is, do I want this to be an internal simulation or an external simulation, or both? In this case, I'm probably only interested in what's happening inside the muffler. So what I want to do is simulate the airflow on this internal cavity only. And so in order to get the program to recognize that internal space, I just need to close up the ends of the model, the open ends of the model where, in this case, I've sort of cut off the tubing coming from the probably the catalytic converter, and then of course the outlet. And so you can model in your own features to close up those openings, of course, like an extrude. But there's also a really easy tool that can do it for you called the Create Lids tool. you can click right here on the Flow Simulation tab in your Command Manager, which will be here as soon as you turn on the Flow Simulation add-in in SOLIDWORKS. And when you click this Create Lids button, all you have to do is click on the face where you want that lid to be created, and immediately it gives you a little extruded body in blue there, and you can adjust the thickness of that, which will of course cap off this internal volume as soon as I add the lid to the other side. So that's it. There's no need to actually model a part with the shape of the air or put a material onto it that way. All you have to do is make sure there's a sealed cavity, and Flow Simulation will do the rest. So here I've got my kind of prepared geometry, and if you want to just confirm that you set up your lids correctly, there is also a check geometry tool which can show you that on the screen. It'll basically detect where the fluid is and highlight it in blue. And as long as you see that kind of bluish shape in the volume there, it tells you what that fluid volume is. You know you are good to go. So at this point we can set up a new simulation and put in all the boundary conditions we would want, like the volume flow rate or the pressures or whatnot, and then have the simulation calculate basically the other parameters that we don't know yet. So let's start with the wizard here. This wizard interface walks you through all the main steps that are important for flow simulation. So for example, I could give this a name, call it maybe 5500 RPM. Maybe that's the performance condition that I want to simulate right now. Maybe that's wide open throttle or something like that. So you walk through the key steps here. The next thing would be to pick the unit system that you want to use. I could use SI units or American units, whatever it may be. And it's also nice that you can customize these units however you want. If you want to look at pressure in PSI, that's fine. You could also look at it in inches of mercury or inches of water or anything else that you may want. Here at the third screen, analysis type, we can pick that internal versus external setting that we just talked about. In this case, I want internal, although if I wanted to simulate the airflow around the outside of the muffler, for example, to look at the heat coming off of it, I could also do an external simulation and include this internal cavity as part of that. So the external will basically just broaden the scope of the simulation. For right now, I'll leave it as internal. And then in order to get some of those acoustic results after I run this, I'm going to make it a time-dependent simulation. And I just put in how long I want to run it for, maybe 1 second of physical time. You can see here also there's some other capabilities I could include, like heat conduction or radiation, if I was interested in the thermal aspects of this. For right now, we'll leave those off. I also need to put the fluid in. In this case, I'm just going to assume it's air, although if I wanted to be as realistic as possible, I could probably mimic the exhaust gases that are coming from the engine. We've got air in the database here, and I can add that right now. But I could also instead do something like carbon dioxide or maybe nitrogen, and I could mix gases, however many I want, to sort of create what mixture I think the exhaust gases will have, rather than necessarily creating a new fluid called exhaust gas. I can simply use some of the existing fluids in the database and put in the right proportions to give me the sort of the average properties that I would want. And that would allow me to see things like whether or not the carbon dioxide or nitrogen is separating out. We'll go ahead and put in our default wall conditions here. That's just going to assume smooth surfaces, although you could put in some roughness if you want. And then we can also put in our initial conditions. Here we've got a temperature of 68 degrees. If I want to assume that we've got hot air coming from the engine, though, I could put in something more like 150. So when I hit finish, I get my project that's been created for me here. And now at this point I can put in the other boundary conditions, like the flow rates that I need, as well as any other goals or other measurements that are important to me, and then I can run the simulation. So for example, if I know how much air is coming from the engine because of the displacement of the engine and the RPM that it's running at, I can create a boundary condition. and simply select that lid that I created. That's where the air is coming from, the header probably on the motor. And so if I know, for example, that volume flow rate, I could define an inlet volume flow condition. Simply punch in whatever that number is. Right now I'm in CFM. I could have changed that to liters per minute or something else if I wanted. Let's put in 200 CFM. And you also have a lot of control over how the velocity profile looks, where it's coming in from this boundary. I could say that there's swirl in the velocity or in the airflow. I could say it has some other vector that's not normal to the pipe. And there's also a useful checkbox called fully developed flow. And if I check that, the incoming velocity at the boundary here will automatically have a fully developed turbulent boundary layer with a parabolic velocity profile. And that would be realistic to match, some existing amount of pipe that the air was already flowing through. So that way I don't have to model in a bunch of extra piping just to simulate how that flow would develop back there. And of course I can also change the pressure and temperature that the air is coming in at if I want to. Here it's got the temperature of 150 degrees that I selected in the wizard. So the air is going to come in from there, and then obviously it has to exit the muffler at the other end. And so I can do another boundary condition for this lid, but I probably don't know any other useful parameters like the velocity. So, and of course the volume flow rate would be redundant. So I need to put in something else at this lid, and in flow simulation what that is called a pressure opening. We simply need to define what the pressure condition is sort of on the other side of this lid so that the simulation knows what environment the air is going into. And that's how it can figure out how much resistance there is in this muffler. So we'll just say there's an environment pressure here, which means that it's open to the atmosphere. And you can see that it's got 1 atmosphere of pressure, which is about 14.7 psi as the default value. Now there are a lot of other conditions I could put into my simulation, everything from heat sources, porous material, etc. But for right now, this is all I really want. And the last thing I need to do then, before I run the simulation, is to put in some goals. Now goals are not a physical condition, but instead they're like a sensor. The goals will help measure whatever properties you're most interested in and give you immediate feedback on the results. So for example, if I wanted to know what the pressure drop through this muffler was, I could create surface goals to measure the pressure at the inlet and the outlet here. You can see I'm just clicking on those same lid faces. I can check the box to measure, for example, static pressure or dynamic pressure or velocity or any other property I want. And I can also create measurements for each of the surfaces I click on rather than all of them together. It's your choice. And so if I do that, now I've got a goal for the pressure at the inlet and one for the outlet. I can measure the pressure drop between the two by creating an equation goal. This lets you put in any kind of function you want, similar to like an Excel function, for example, just a simple addition or subtraction, to create your own type of measurement. So if I go to equation goal, I know that the pressure drop is the pressure at the inlet minus the pressure at the outlet. And I simply click those goals and type in minus sign here, and I can give it a name, P drop, to make it easy to track. In addition to that, there's any other number of goals I might want to create. And if I want to examine the acoustic properties of this product at some point, I will be able to click any of these pressure goals here to measure it, or of course I could create another pressure goal either at a certain point somewhere in the model or even on all of the internal faces of the model, whatever I want. And that will allow me to see what the acoustic power is at those locations. Of course, I might also want to click the outlet and say, to give me a goal of average velocity, let's say, or even turbulence. Now, as far as the meshing is concerned, this is the aspect of the flow simulation that the users of the tool most like, which is that the mesh is what we call a non-body fitted mesh. So it looks like this XYZ Cartesian grid, and it doesn't have to fit any elements into the actual faces or edges of the model, which means that It's very seamless to create the mesh. Even if you want to start your analysis with a very coarse mesh, you don't have to worry about mesh errors or figuring out what size you need just to create the mesh, or doing a lot of simplification on your parts just to get the mesh to work. Really all that's necessary is to pick some level of accuracy on the mesh slider here, which as you can see changes the size of the grid, and then put in this option here called minimum gap size, which is basically the smallest level of detail that you want to make sure the mesh captures. For example, in this situation here, the perforated core has these metal holes in it, so I would put in, whatever the diameter of those holes is, let's say 2 millimeters. Now I've got my finished one over here. Here's a transient simulation that I've run. And so I'll go to look at these full results in just a moment, but just so you can see what it looks like to solve something, I'll go ahead and hit the run button here. This is going to generate the mesh, and it's actually going to refine the mesh by splitting those cells you see, let's say 1 or 2 times, to capture the geometry better. So in other words, to fit inside those little holes or other areas. And then it's going to immediately do the solve. And I could run this on my local computer, as you see right here, or I could also offload the job to another machine located on the network. For example, another server here in my office. And I can also choose how many CPU cores I want the simulation to use while it's running. By default, it will use all of them, and so this solver is multi-threaded. It will take advantage of additional CPU cores. So here's the solver window that's popping up. It's generating the mesh. And you'll get a number of cells that it reports, which of course controls how long it's going to take to run the simulation to completion. And then once the solver begins, you're going to start to see some partial results pop up on the screen over time that you can examine while the simulation is still being computed. So here you're seeing a goal plot. Those are those key results that I entered in that I was curious about. And in this case, what you're going to see is just literally the values over time because it's a transient simulation. If this was a steady state simulation where I didn't care about what's happening over time, instead what you would be seeing is just the gradual progression of these goals until what we call convergence. Convergence meaning that everything has achieved equilibrium, and we're going to see what sort of the constant flow rate or other constant temperatures or other properties would be. So I'll go ahead and stop this. And I don't need to save those results. Let's go look at the final results that we calculated over here in the previous study. I used a somewhat coarser mesh the last time, so when we ran this one before, it only took about 3 or 4 minutes to solve. You can see right there. That was with about 15,000 cells, which would be good for a first pass simulation. And so when your analysis completes, the first thing you normally want to do is go look at those goal results. I can pop those up here in a goal plot. You can see I've got things like turbulent intensity or the pressure drop and velocity. And so in this case, for example, this is sort of the baseline design here. I can figure out that I've got, for example, about 10 inches of water pressure drop. I've got an average velocity of about 300-something feet per second. I've got about 30% turbulence, meaning that that's the portion of the energy in the flow that's due to turbulence rather than just the free stream or laminar flow. And I can examine visual plots to figure out why I'm getting those numbers. Everything from, for example, a cut plot, which is basically like a section view and allows you to look at pretty much any parameter you would want on a plane somewhere inside the model. Here we're looking at pressure, and we can see right away there's kind of a large amount of restriction here when this angled exhaust pipe goes into the muffler. That's kind of where there's the biggest pressure drop. We can also see the mesh. You can see how it refined itself to capture those holes in the core. And of course, we can also see things like these streamlines, which will help us figure out where there's recirculation or dead zones. And in this case, you can see that because of the diameter change, there's a fair amount of separation that's happening, which also shows up better if we look at a velocity plot instead of pressure. So these are the types of things that might help influence how you adjust the design, in order to maybe remove some of these inefficiencies or try to highlight where you can remove the most restriction in the flow. And of course, the idea would be that you'd make a change and run the analysis again. We also, of course, can do things like show the flow trajectories in 3D, and we can even animate those. You can save these things out to videos, GIFs, or whatever you want, and send them over to your colleagues to help visualize it better. Now, in this case, I just did another example where I made another configuration of the model, and we just changed the diameter dimension on this metal core. You can see right here that we changed it down to 1.2 inches, which is a simple extrude feature. And at any time then, I would be able to click on my flow project that I made and hit the clone button, and that copies the entire project with all of the setup over to this new configuration. And I can simply hit the run button and recalculate the results and see what happens. And the really nice thing about doing it this way, where you've got two separate projects side by side, is that you can use the compare tool to actually evaluate which design is better in different ways. So for example, I can click compare on the drop-down menu here, and I can grab any of the different plots that I want to look at, for example, the cut plot or those goals. And rather than clicking back and forth multiple times, I'll be able to look at the results side by side. So we can see there, for example, on the right is the second revision, revision B, and it looks like the pressure drop observed at that bend is a little bit lower than the first time. I can also look at my goal plots, and I can see that, interestingly here, it looks like my pressure drop did go up when I made that change. So overall, there's a little more resistance, which kind of makes sense because I've decreased the diameter, but I've also increased the velocity at the exhaust point, which might be helpful for scavenging effects in a header. I've also decreased the turbulence, so more laminar flow might be desirable for one reason or another. In addition to that, if acoustics were an important aspect of what you want to look at, there's a new functionality in Flow Simulation 2018 called the FFT, or Fast Fourier Transform plot, which will help evaluate some of these things. So we might have just done our compare results here to look at velocity or pressure drop or whatnot, and we might have decided that this newer design is better in some ways and worse than others, but we could also do the comparison for the acoustic results. And so the way you would generate this type of FFT plot is, like I mentioned a minute ago, you need to make sure you have a goal created for pressure somewhere in the model. In this case, I've got one just on all the internal faces of the part, as you can see here. So on the metal core, on the actual tubing coming in, etc. And if I go here to the FFT plot option, which I've got created down here, I simply click on the goal that I created there so that I know which faces I want to measure. And then I can select what type of audio property I want to display in the graph, whether sound amplitude or just sound pressure level or PSD, power spectral density. And what this will do is it will automatically convert the pressure results over time into the frequency domain, which means when I click the show button, instead of something over time, I actually get to see this amplitude level in decibels at different frequencies. So here I've got a really good idea of the sound profile of the air inside the muffler. So for example here, this is showing that at about 200 or 289 hertz, 300 hertz or so, I've got about 91 decibels of sound. So the most prominent sound is going to be in this low end here of maybe 200 to 300 hertz, and then it drops down somewhat, and throughout most of the range, the decibel level is more around 73. Now that's just the decibel level of the air, so of course when you factor in that sound dampening materials that might be in the muffler design, that sound will probably be reduced. And Flow Simulation doesn't really get into that world of structural acoustics, but as far as how much noise the airflow itself or other fluid is generating, that's what this plot will show you. And in fact, if I do a comparison there between those two plots, we can see that that design change that we made also shifted the noise profile. So Rev B is the blue one, and you can see that it's, especially at the low end, it's louder overall. So maybe for that reason we would decide to go back to the original revision, or maybe make another change that wasn't as drastic. Just another thing that can help influence these trade decisions that you make during the design process before you have to go actually manufacture anything or do a noise test on it. Let's look at one more case study. Here's a short ram intake, something you probably would see more often in an automotive application. Of course, the point of a short ram intake would be to increase the amount of airflow you can get into your engine, particularly in a naturally aspirated engine. And so one of the key things there to look at might be how restricted the filter is, the cone filter itself. And so we can account for that with the porous media functionality in flow simulation. There are a variety of ways to define the properties of the porous media, but basically it will allow the fluid, like the air for example, to pass through it, but at a restricted rate, depending on the permeability of the material. And you can put in the properties through one of these methods here when you are creating the porous media in the engineering database. And then once you've got the properties dialed in for that permeability of the material, you can apply it to any shape you want, whether it's a cone filter or just a flat screen filter or anything else. So let's look at that model as well. I'll go ahead and close the muffler here. Open up the ram intake. And for this one here, we're going to have another internal analysis because we really only care about what's happening inside the piping here. Although in order to make sure I'm capturing what happens as the air passes through the filter, I still need to make a lid somewhere, and so I've made it on the outside of that filter right here. Just kind of a sort of a conic cylindrical shape, and that's going to be where my boundary condition goes. But I could have also done an external analysis here where I actually simulate, a big region of air all around the outside of the filter. In fact, I might even want to model in some of the other components in the engine bay, if that's what I'm trying to simulate. So of course we would go through and create another project for something like this, just to recap it. And this one is another internal analysis. And in this situation, we've turned on heat conduction so that we can figure out what the temperature in the tubing is. Maybe we're worried that the heat from the engine bay is going to raise the temperature of the air by the time it gets to the intake manifold. We've got air in here as our fluid again, although it could be anything else. And we've also now got a solid material defined. I'm going to assume that all of these components are made out of 6061 aluminum, which has a fairly high conductivity. So here we've got an outlet volume flow rate this time leading to the engine. Again, probably just based on the amount of displacement in the engine. And I've got that environment pressure condition on the lid around the cone filter. Again, that just describes what pressure the surrounding air is at, so we can figure out how much resistance there will then be inside the geometry. And then the key on this one is the porous media. You can see right here that we've got a porous media definition on the actual filter part itself. The way you would do that is simply go to porous medium and click the part, and then select one of those material definitions from the library. There are a few built into the Flow Simulation Engineering database, and including this UAF category, which is available as part of the HVAC add-on module in SOLIDWORKS Flow Simulation. That one just has some metal mesh filters, polyester filters, and a fair amount of unifoam filters, which you can either use or just copy and modify as far as the properties go. I'm going to use this half-inch 80 ppi filter, which is basically like a very high-res filter that will filter out pretty small particles. And again, if you wanted to go look at the properties of that in the database here, this one is defined by the pressure drop, velocity, and dimensions. In other words, some real-world data that you might gather from a flow bench somewhere, and you would put that data into a table here and it generate this type of curve so that it knows, depending on what kind of flow velocity you have going through that porous material, it knows how much resistance there should be. So this particular material had about 600 pascals of resistance at 5 meters per second. And that can be extrapolated to all different kinds of flow conditions. And again, like I mentioned, there are other ways to define the porous media if you wanted to create your own. If you have your own type of material, you can define it as a collection of pore sizes, like, for example, little straws stacked up. You can make it dependent on velocity or flow rate. And basically use whatever kind of real-world data you may have. You can even include the heat transfer properties of the porous material if you want to assume that it's taking some heat out of the air. So here I've got my porous media set up. I've also got some pressure conditions similar to the previous example, measuring the pressure at the inlet and outlet to figure out how much of a pressure drop there is, which I can create with my pressure engineering goal here, one minus the other. And then if I ran this, I could of course take a look at some similar results to the last example, whether that's a cut plot of velocity. I might want to drag that back and forth to figure out kind of what that profile looks like. Maybe I want to look at the flow trajectories in 3 dimensions. This is showing the air coming in fairly evenly through the filter, and then a little bit of swirl being added as it goes around that elbow, which I could animate, of course. And I also could look at a surface plot, which will show the results of the simulation on the faces of the model. So, for example, if I want to look at temperature here on the outer faces of the exhaust, I could see whether or not there's a hot zone or any significant temperature delta. In this case, it doesn't look like there's a big difference. I could use the probe tool and actually confirm that. And this is showing me that maybe there's a range of maybe like 5 degrees Fahrenheit around this thing on the different outer surfaces. So maybe that means that the internal airflow is high enough that it's keeping this cool. And of course, I could examine a comparison. In this case, maybe removing the cone filter, just to see what it would be like if I didn't have any restriction at all. And of course I could compare those results with the same tool that we used before, and not only look at the goals, but also look at an animation or anything else. In this case, when I removed the filter, it looks like the pressure drop did go down, but not a whole lot. So that's telling me that the filter itself wasn't adding too much restriction. And it also is interesting that removing the filter increased the amount of turbulence. So the presence of the filter seems to have been kind of keeping the airflow more laminar as it goes down that bend. Also, you can look there, we had a surface goal for temperature at the outlet, which in this case would be where it connects to the intake manifold. And that temperature was only 100.3 or so degrees. We assumed that the air coming in was 100. So that means there was minimal temperature rise of the air going through the ram intake. So that means that this airflow was sort of high enough to negate any worries about heating from the engine bay or the external temperature coming in. And of course, if you wanted to explore other aspects of that, like putting in a heat shield or putting in insulation or maybe a different flow condition like a lower flow rate, you could examine all of those parameters. Of course, what we really looked at here is a small set of what you may want to do with flow simulation. You could examine not just internal engine components like what we looked at, but for example, flow in an intake manifold itself and the header of the exhaust. Maybe you'd want to do a simulation of the heat exchanger like a turbo intercooler to figure out if you can lower air temperature more effectively before going into forced convection. You could look at aerodynamics of the vehicle itself, whether that means just pressure plots on the surface of the vehicle or streamlines as it goes around. Even design things like pumps, for example, that like a supercharger itself, you could figure out how much pressure boost is available from that supercharger, or maybe even hydraulic fluid manifolds in something like the brake system. So as long as the type of fluid can be entered into the software, which we generally have the capabilities for, you can simulate a lot of aspects of that type of a product in the same program. And there's quite a few companies that have used flow simulation for that type of an application and others. I think one company called Center Rock, which used it for downhole drilling. And of course, we here at Hawkridge are pretty experienced because of all the different customers that we work with in these various simulation tools. So we have a pretty good understanding at this point of what the best tools are in each of these situations, and more importantly, how to use them. For example, whether or not you can really get the key results or that you would need to make the important design decision that you want based on the capabilities of the software and what your existing process is. So we would encourage you to reach out to your account manager and us as well, who can be brought in, and we can have a pretty upfront discussion that helps make sure you're going down the right path. And of course, once you get the software, we have the expertise to give you all the training you would need, all the personalized mentoring or consulting you might want to learn how to run your particular simulation the best way you can, and even doing consulting services if that's something you were interested in. We can provide the results of an analysis for you even if you don't have the software. With that, if there are any remaining questions, I'll try to get to them and answer anything related to this presentation or about flow simulation in general. Otherwise, thanks again for attending. I hope it was informative for you. If you have any follow-up questions later on, feel free to email me. It's damont@hawkridgesys.com. Or you, of course, can always contact support at hawkridgesys.com or go to the website. Thanks again.